Hardy-Weinberg. This is a really, really helpful way to show that evolution happens. So just kind of a brief overview. We can't ever prove that something happens in science. We can't prove that evolution happens. We can just gather a ton of information to consistently support our theory. So the idea is, Hardy and Weinberg came up with this idea that equilibrium means nothing ever changes. The allele frequencies, things that are getting passed down generation to generation, the traits, all of those things would never, ever, ever change, and that would be equilibrium. So they set up a hypothesis saying, we think that equilibrium will always happen. And then guess what? Every generation is different from the generation before, right? You don't look exactly like your parents. You didn't inherit the exact same types of traits. So what we do here is we disprove, the Hardy-Weinberg equation disproves equilibrium. If equilibrium means there's no change, what we're really saying is change happens from generation to generation, and guess what? That's our definition of evolution. So we're actually showing that evolution happens mathematically. Now I try to make this really easy for you, so the populations will always be 100 to make the math easy. You're always going to start with q squared. I'm going to show you what that means in just a second. But here's our scenario. So we are zebra rescuers, right? We live in Africa and we want to save the zebra population. So we have 100 zebras at our little sanctuary. And we notice that 25 of them have the rare spotted coat, which is a recessive mutation. And we want to figure out the frequency of the stripes that we normally see and the spots, which are new. And we want to then be able to trace this generation after generation, and as long as the numbers are different from generation 1 to generation 2 or 2 to 3, that is going to be showing us evolution at work. So we have two different equations, okay? Don't let it scare you. It's very simple. Make sure that you realize what these variables stand for. We have p squared. Now the reason we're using p's and q's is just think of this like algebra, right? Solve for x. X just means an unknown. But since we cover genetics, we have X and Y chromosomes. We don't want to use X and Y because we might get confused whether we're talking about sex chromosomes or not. So we're using two letters that just mean unknown. P here stands for, P squared stands for individuals, so our zebras that are homozygous dominant. So they would look, I'm not going to use Z because they don't look different, uppercase, lowercase. Let's use R. So they would have alleles like that. Okay, there are two here, so there would be two P's. Let's hop over here. Q squared are all the individuals that are homozygous recessive. So they would have nothing but recessive alleles. And then if we have two PQ, that means a P and a Q. We have both dominant and recessive. That would be our heterozygous zebras. Okay? These are the only three genotypes that exist. Homozygous dominant, heterozygous, homozygous recessive. So that equals 100% of the population. We're going to write that as 1.00. Now here's the problem. I don't know if my striped zebras that are showing the dominant stripes, I don't know if they're fully dominant or if they're heterozygous and carrying a spotted trait right here. So I have to actually break these two apart. And the way I do that is a second equation. I'm just going to look not at zebras but at their alleles. Anytime there's just a single P, that stands for a dominant allele. Anytime I would see a dominant allele, and Q by itself is the recessive allele. Okay? So there's 5 steps to solving this. You're always going to want to write all 5 of them out. That way if you mess up, I'm going to be able to tell you exactly where you went wrong. Plus, you're going to get full credit that way. If you just put an answer, I have no idea if you actually came up with that answer yourself. So, as I said over here, the first thing you're always going to start with is Q squared. Why? Because I'm sitting here looking at my 100 zebras, and I can count the 25 that have spots. I can actually see them with my own eye. Just like if I had 100 students in my classroom, and I wanted to know who was fully recessive and left-handed, I could count you. I could say everybody start writing, and I could count how many of you were homozygous recessive. So I'm always going to start with Q squared. Q squared is what's given to you in your problem. So Q squared is 25 out of 100 zebras, which is 0.25. Okay? Don't be a hero. Use a calculator. Okay? Nobody's watching. Just use a calculator and get the right answer. Okay? Put in 25, divide it by 100, you get 0.25. After your decimal, you always want to have two numbers. If you only have one number, you're going to want to add a 0. That's really going to help you visualize the math and make sure that it's correct. So that means 25% or 0.25% of my whole sanctuary are my spotted recessive zebras. Now I got to break these guys apart. So I'm going to have to use my second equation. The way I'm going to do that, I'm going to go from zebras to just the spotted allele, from Q squared to just Q. And the way that you do that is you take the square root of what you just found in step 1. If you're using a phone, when you're in the calculator, turn it to the side and you will see the square root button. Okay, if you have any questions on that, let me know. So we're going to do the square root of 0.25, and that equals 0.50, not 0.5, because then your brain thinks 5. No, this is 0.50, 50%. So my Q value over here is 0.50. And it's very important that you write these equations out and you kind of fill it in as I'm doing, okay? Especially if this is new to you, you really want to make sure everything you're doing is really just keeping track of where you're going so there's no silly mistakes. Step 3 is pretty easy. I know that P and Q together have to equal 100. And I've just said that Q is 50. So what does P have to be in order to get to 100? Well, P must equal 0.50 as well. So I have a very even split here. In this zebra population, I see the dominant allele half the time, 50%, and the recessive allele, 50%. So now that I've separated my alleles, I can come over here and plug these guys in. So step 4, now that I have my dominant allele, which is just P, I want to go back to my zebras, which are P squared. So what I'm going to do is I'm going to square it. You can either use your calculator or you can do 0.50 times 0.50. It's the same thing, okay? So 0.50 squared or 0.50 times 0.50. Plug that in your calculator and it also is 0.25. So I have a nice even distribution. 25% of my zebras are fully striped. Absolutely no spotted gene there at all. 25% fully spotted, no stripes at all. Now this just leaves here. These are my troublemakers. These are my zebras that look normal, they got stripes, but guess what? They're carrying the spotted trait. So we want to know if they're going to pass that down potentially in the future. So I like to plug in here because I'm not a huge math person, right? So basically, I already have 25 accounted for. I got another 25 accounted for, which leaves me with 0.50. Now, what do I always have to get to? 100. So what does this have to be to equal 100? It has to be 0.50. The other thing you can think of is if you're really hungry and you're at the vending machine and that candy bar is $1, left pocket has 25 cents, you got a quarter there, right pocket you find 25 cents, and you're like, dang, I only got 50 cents. Hey, I need to borrow 50 cents from someone, I'm hungry. That's what you're missing here, okay? So 2PQ is going to be 50. Now what does this mean? This is the distribution of alleles in this one population at this point in time. If I came back a couple years later and I looked at all of their babies and I did this math again, do you think I would get exactly these numbers? No, I'm not, because change happens. Okay, change happens. And especially when half of my population is carrying the spotted allele, there's going to probably be more spotted zebras because they are going to be able to pass that down. So we are looking at the distribution of frequencies to then kind of look at them over generations. And that is going to disprove equilibrium and show us that evolution is occurring. One last thing I want to show you. This sometimes helps people. If not, no harm, no foul. But basically, we can look at this as a Punnett square as well. If you're dealing with your P and your Q alleles, which are the only alleles we have, and you basically put them in a Punnett square, you get a P squared. You have two PQs, and you have a Q squared. That's where we get our equation from. Okay, so Punnett squares and Hardy-Weinberg are actually connected. Okay?